So the blue line that you see is actually d square by dv square of bv. So it's not as bad as you think, because fiber optics commercial, which is used for communication technology, is full of empirical relations, right? You don't really have to solve all this electromagnetics to get your B versus V curve, right? What you can, there's an empirical relation for this B versus V curve for single mode region, because this is a highly nonlinear curve. So you can kind of find out empirical relations, polynomial fits for specific regions of V. So there exists one such empirical relation for an SMF which is coming to your rescue. You will know that this B is approximately equal to A minus B by V the whole square, where A is equal to 1428 and B is equal to 0.996. Because B versus V is a universal curve, it does not matter what kind of fiber you are using. A part of that curve you can fit, and this is the empirical relation, and this relation is going to be useful, because from this relation I can find out what is BV, I can find out what is dB by dV, right. I can find out this, and then I can find out d by dV of this, and then I can find out d square by dV square of BV, and that is what I have plotted. Okay. So I just calculated this, because I have a analytical relation between B and V. I just calculated this. It came out to be something like minus 2B divided by V square or something like that, right. So that is the plot I have done. And if I were to now do it for a specific wavelength, I were to calculate. So for example, I have given this 1.45, N2 is this, A is this. How do you find waveguide dispersion at 1560 nanometer now? You have to find out first what is the V number, and corresponding to that V number you find out what this number is, and from that you can now go ahead and substitute in this and calculate what is a waveguide dispersion. Okay, you will get it as some picosecond per kilometer nanometer. How do I find material dispersion at this point? Remember, material dispersion is also acting at the same time. How do I do that? What do I need for material dispersion? D square n by d lambda square. It's all second derivatives is what we keep needing, right? So that data I have already given you, something like 0.004 at 1550, assume that is the same at 1560. So you can calculate that, then you can find out what is the total dispersion. So this is an exercise that you need to do. So it should come out to be something like this. Waveguide dispersion turns out to be minus 5.94, material dispersion turns out to be plus 21.93, and the total dispersion is so plus 15. What is the meaning of this minus and this plus? Physically, what does it mean? If I have minus dispersion and I have plus dispersion. See, when you define dispersion, you define delta tau, which is d tau divided by d lambda times delta lambda. If this delta tau is negative, what does this mean? In whatever sense you defined your delta lambda, upper wavelength minus lower wavelength. Suppose you defined your delta lambda as upper wavelength minus lower wavelength, and that is a positive number, and if delta tau is a negative number, it means that the upper wavelength is slower than the lower wavelength. The higher wavelength is slower than the lower wavelength. But if you had defined your delta lambda as the other way around, correspondingly it is different. So it is just telling you which wavelength is propagating faster and which wavelength is propagating slower. Typically in a prism, when we take glass, we talk about material dispersion, right? Prism splits white light into 7 colors because of material dispersion. And what is the nature of dispersion there? As you go from red to or violet to red, from one end to the other, right? Let us talk about visible spectrum. Which color deviates the most? Violet deviates the most. Refractive index of violet is the highest, that is why it deviates the more. So, the lambda of violet is the lowest, refractive index is highest, and for red the lambda became larger, refractive index became smaller. So, as you went from higher wavelength to lower wavelength, which is red to violet, your refractive index changed by a lower value to a higher value. Okay. So, that is why the time taken by red is fast when compared to the time taken by violet. Now, that is called normal dispersion. So, normal dispersion means, actually it is got used in the context of the English word normal dispersion. Normally what you see is normal dispersion. That is when you have n increases when lambda, sorry, n increases when lambda decreases, that is correct. So, easy to remember is prism. Anomalous dispersion is when you have the other way around, right. So, opposite of this is anomalous dispersion. So, the beauty is you can make the total dispersion as normal dispersion or as anomalous dispersion by controlling the waveguide dispersion. You can make the total as positive, you can take the total as, make the total as negative by controlling waveguide dispersion. How do you control waveguide dispersion? Now, that is very straightforward, because your waveguide dispersion is depending on your BV, or in other words, waveguide dispersion is depending on your value of V. So, you can still be single moded and control the value of V to figure out whether control by all how much you can alter the waveguide dispersion and thereby control the total dispersion. So, we will take an example here. This similar fiber, this is a standard single mode fiber, right, commercially used standard single mode fiber. N1 is, I have given up to 6 decimal places, because that is going to affect the value of the material dispersion and waveguide, not the material dispersion, maybe the waveguide dispersion. N1 is this number, N2 is this number, which is smaller of course than N1, and A is 4.1 micrometer. You see this line shows the material dispersion. Okay. The waveguide dispersion is negative and it is shown by this as a function of lambda. It is calculated as a function of lambda. We know n as a function of lambda, and we had shown you the dn by d lambda and d square n by d lambda square and so on, right. So, in this range of wavelength I can calculate what is the material dispersion, and I can also calculate what is the waveguide dispersion for this range. Assuming all this, this fiber is single moded in this entire range, and this fiber, if you calculate the V number, it is going to be single moded in this entire range. Okay. So, now the total dispersion is this if I were to now put a purple line, the total dispersion is here, and the total dispersion is negative in this region, total dispersion is positive in this region. Okay. And why did that happen? That is because material dispersion crossed signs here. What would you want the fiber to have? Would you want to have the fiber to have large dispersion, or would you want the fiber to have a small value of dispersion? What is the ideal value of dispersion? 0, because if you have 0 dispersion, there is no delay, there is no spread. So, if I were to propagate long distances, ideally I would like to have 0 dispersion, right. And for this kind of fiber, the 0 dispersion happens around This is actually not drawn to scale, but this is something around 1325 nanometer. That is a zero dispersion wavelength for a standard single mode fiber. But we still seem to be preferring to do 1550 nanometer propagation, right. Commercial long haul communication is, we always talk about 1550 nanometer. 1310 also we use, it is zero dispersion, but we always say commercial long haul link we prefer 1550 nanometer. Why so? Even though the dispersion, so look at 1550 nanometer, so this is roughly at I think 13, this is 1250, 1300, 1350, 1400, 1450, 1500, roughly at 1500 the total dispersion is 15, around 1550, let us say around this value, it is actually 17 picosecond per kilometer nanometer. This is a number to remember if you are a fiber optics engineer. 17 picosecond per kilometer nanometer is the total dispersion of a commercial standard single mode fiber. Why 17? I mean, it just turns out it is 17 from by calculating all this material and waveguide dispersion at that. But even though it is 17 picosecond per kilometer nanometer, I would still prefer to do long haul links with wavelength at 13, not at 1300 but at 1550 nanometer. Why so? We have amplifiers at 1550 nanometer. So, but before that I have to say, why do we need amplifiers at 1550? Why are we talking about amplifiers? You remember your attenuation curve. Your attenuation as a function of lambda was hitting a minimum at 1550 nanometer. So, you are interested also not just in dispersion, you are interested in power budget of the system. So, if you are transporting long haul at 1310, what happens is the signal accumulates much more loss and there are no fiber amplifiers at 1310 nanometer. The EDFA that you are using in the lab also, which are currently used in the communication system, that works magically for the band. It has, as if nature has given us a material called erbium, which can be doped in fiber, and it amplifies in that 1530 to 1560 nanometer range, which incidentally happens to be a low loss region as far as silica fiber is concerned, which is why the invention of EDFA, I am sure it is going to win a Nobel Prize sometime. It is very, very important because otherwise our long haul communication link would have been really difficult. Of course, you could have used a semiconductor optical amplifier, but that is more noisy and so on. Raman amplifier is another amplifier that is used, but they are used only for some specialized systems. The reason being, the pump that is required for Raman amplifiers, the amount of power that you need to put into the system to initiate Raman process is really high. So, it is not used in regular networks. You have some specialized undersea networks where there is no operator who is going and digging every day, right. For those kind of networks you use Raman amplifiers, but not for regular commercial communication systems, let us say terrestrial communication systems. Because when you have high power, then power handling becomes a problem. The operator has to, the person who is going and installing in the field should wear protective glasses and so on, right, and it cannot be exposed. Those are very difficult to implement practically. So, amplifiers are available at 1550, so you use 1550. Now, the question we want to ask is, okay, I have a constraint that I have to use 1550 nanometer as my communication wavelength. Can I shift my dispersion, zero dispersion to 1550 nanometer? As a fiber optic engineer, what should be your answer? Obviously yes, because how do you engineer a fiber now with zero dispersion at 1550 nanometer? You have a very powerful control with you, which is DM. Can you change? Material dispersion is a material property. If you want to change DM, you have to change the material from silica to something else, and that is not acceptable because silica is proven to be the best material for optical fiber. So, the problem you have is you can't do anything with this. but you can do a lot of things with waveguide dispersion, because waveguide dispersion, as we were seeing, it's dependent on the core dimension, it's dependent on, so I can keep everything else the same, but I can play around with the core diameter to change my waveguide dispersion, or I can change the refractive index contrast, or I can change the cladding refractive index. All these parameters I have in my hand to change my waveguide dispersion. So the question is, by changing my diameter we may end up with multimode. Of course, what should I do? I should ensure that all these changes I am do, while I am making all these changes, I should keep my V number less than 2.4. So what was your waveguide dispersion? Let us take a quick look at it. What can you change? This was minus N2 by C delta 1 by lambda naught V d square BV by dV square. You can change V, you can change N2, you can change, okay, you can change N2, you can change delta, where is the, and you can change V, which has the A in it, right. If I were to increase, if I were to make dimensionally or in magnitude dV to be a large number, what should I do? My A should be larger. If my, but when my A is larger, of course my V is changing. If you have to also worry about this relation at that time, right. So it's not very straightforward to predict what it is. You can now run it for different, you can actually analytically calculate it for different possible values of A, and then ensure that the V is still less than 2.4 and still achieve a desired waveguide dispersion. So that's what people did, and they created what are called as dispersion shifted fibers, where the zero dispersion is shifted to 1550 nanometer. So the waveguide dispersion, if you see, they change the magnitude. So in the previous graph, the magnitude, this is the zero line, and here was the waveguide dispersion, and now they made that to 0 is crossing at 1550 nanometer. So you made the waveguide dispersion really large to compensate for the material dispersion. So when fiber optic technology was evolving over the years, in 1980s when people started doing long distance communication, and that's when they realized the problems with dispersion, and that's when they started looking at how to make a fiber design now to change the dispersion properties and so on. One of the things, of course, you should remember is that when you are changing N2, the dopant concentration changes, and what happens when you change the dopant concentration? You should also remember that the attenuation may change with the dopant concentration. So it should not change your attenuation too much also, right. Core dimensions may decrease. When core dimensions are decreased, then your coupling efficiency will go poorer and so on, right. So all those issues you have to make sure that you are taking care. So but people thought that this was the best solution to have. You have EDFAs at 1550, so you can amplify, you can make zero dispersion at 1550, so you don't need repeaters for a long distance, very long distance. The pulse is not going to spread, its attenuation can be compensated with EDFA. So you ended up with a very ideal system, which is dispersion shifted fiber, right. But this dispersion shifted fiber was developed probably in 90s, but we still don't use these dispersion shifted fibers in the field. We still use this fiber in the field. What could be the reason for that? Diameter is not, that's not really the issue. Even though I said diameter is very small, so long as you are maintaining the V number to a reasonably good number, the mode profile will remain the same, right. So that is not the reason. There is another reason that prevented DSF not to be deployed. In fact, it is said that it was deployed in Japan for very long distances, and they had to really pull it back and replace it with regular standard single mode fibers, simply because the fiber started behaving as a nonlinear medium. Now, when there is no dispersion, what started happening was all these colors will start mixing with each other like in any nonlinear medium, and even when there is dispersion they would mix with each other, but because of dispersion all these colors are walking off, they have a certain walk off, so that there is no phase matching that is happening for the nonlinear process. Whereas you took away the dispersion, you made it zero dispersion, the fiber became a very ideal medium for nonlinear processes. We will talk about nonlinearity a bit later, where you will realize that the fiber is an excellent nonlinear medium because the intensity of light, even though the power that you propagate inside the fiber is small, the intensity of light is power divided by area, and area being small, intensity is actually large. And so, if you can slightly increase the power, the intensity becomes large, and so fiber becomes, all the nonlinear properties will start coming up. And the reason why you do not see nonlinear property in regular standard single mode fiber is because of dispersion, because of the fact that the different colors, they mix to produce additional colors, but they have walked off, which means they go out of phase, and when they are out of phase the mixing is inefficient. So, which is why the zero residual dispersion leads to a large nonlinearity, and that resulted in the fact that these DSFs are not useful. You went back to standard single mode fibers. In fact, there was another design which are called as dispersion flattened fibers, where you say that the commercial range, which is like around in this range 1350 to about 1550, the dispersion is almost flat, the value of dispersion is almost flat. When you do that, and that is not zero, so you keep a small residual dispersion in that region, so that there is a walk off, and you keep it constant, so that you do not have to worry about different dispersion managements at different lambdas. But it turns out that so you may not understand this term 4-wave mixing product, because this is a nonlinear phenomena. We will talk about it later on when we do nonlinearities. But it turns out that this dispersion flattened fibers are quite expensive, in the sense that people are managing things without these dispersion flattened fibers. Dispersion flattened fibers would also require manipulation of the core material, and they become slightly more lossy than a regular fiber. So, this was also not very popular for commercial applications, but for some specific niche applications you want to, for instance last year's Nobel Prize was for a femtosecond laser, where the chirp of the pulse was compensated with appropriate dispersion, right. So, for such specific applications you can use these dispersion flattened fibers and dispersion shifted fibers, and something called as dispersion compensating fibers, where the dispersion is very large and so on, right. So, the key idea is the ability to manipulate the total dispersion by manipulating the waveguide dispersion, right. So, you should be able to know how to change the waveguide dispersion, so that you can control the total dispersion. So, that brings us to the conclusion on the dispersion in standard single mode fibers.